there were channels for sodium and channels for potassium, right? This protein is a channel for protons. And as the proton gradient builds up, the protons begin, by diffusion, begin to pass through this protein as a proton channel. And as they pass through, they activate the enzyme part of the molecule, which starts adding phosphate groups to ADP. So it is, in fact, a proton gradient that causes the ATP synthase to put the phosphates on ADP. Now, you may think that much, but I'm telling you, you will never in your life hear a more concise explanation for energy production than that. Glycolysis, followed by the citric acid cycle, followed by the electron transport chain, or oxidative phosphorylation. Now, we started this story, whenever we began this story, we began our story by talking about how muscles really like to burn lipids. Okay, so I like to bring up a couple of other side notes here at the end of this story to get you warmed up for where we are going later in physiology. So I started all this story before by telling you how the muscles use lipids and sugars to make energy. And I'd like to return to that lipid story for just a moment in order to emphasize something else in the human body about oxygen and carbon dioxide and energy usage, and so you can get a big picture thing about what's going on here. All right, so although this picture is early in the early chapters of your book, the Merib text, the Holz text, none of them are going to take you into the place where I want you to go. So you need to get this from me. All that I've said today is written out beautifully in the Merib text. So you're welcome to read that as you're doing your studying. If you miss some of this proton gradient story, it's great. The Merib text is beautifully written. Okay, but this story, you know, the big picture story about muscle stuff and the big picture story about lipids on the backside of this is not told. But it's important for reasons that you can't know yet, but reasons that you'll understand in time. Okay, so when we look at this picture right here, we can see that, that in the production of ATP, so this is intended to teach lipid pathways, in the production of ATP, I have the citric acid cycle here, so I must have in this energy production story the electron transport chain. So you recognize here the acetyl-CoA, right? So if I had just lopped all this part off of the picture, and I said, look, students, acetyl-CoA joins with oxaloacetic acid and forms citric acid, and the citric acid cycle runs, and then the electron transport chain goes, and what we find is carbon dioxide is a product of those reactions, and lots of energy. You would have said, I got you, Wade. I heard you say that a minute ago. Okay, but what I've added to the top of this is the story of lipids. So over here, you can see the glycerol glucose story. That is a diet story that we will talk about in the digestive system. Glucose and lipids are related? Yes. Okay. But this is the story I want to tell over here because it helps me bring up carbon dioxide and acid-base balancing in the human body. Okay. So I have to teach you to do this properly. I have to teach you a basic respiratory fundamental fact of life that you can't get unless you hear it from me here. All right, so here it is. Carbon dioxide in the human body means acid. Carbon dioxide means acid because when carbon dioxide is in water, which we are full of, it turns into carbonic acid. So carbon dioxide levels increasing equals acid levels increasing. Now, you learned in chemistry, I'm hoping, at some point in your life, that to define something as an acid simply means that you are increasing the number of free hydrogen atoms. So as the hydrogen content increases in a solution, the pH of that solution gets lower. So if you're measuring pH from 1 to 14, am I okay saying this? 7 is neutral, 1 is very acidic, 14 is very basic. Stomach juices are around 2 or 3, very acidic. Am I okay with that? You've heard of the Sorensen scale at some point in your life. 1 to 14 acid-base scale. 7 is right in the middle. The human body runs all of our reactions, metabolism, the whole 9 yards. We run efficiently at a pH of 7.4. 7.4. Now, is that acidic or basic? If 7 is neutral, 1 is acid, and 14 is base, then 7.4 is basic. So our bodies live on the base side. Reactions in us occur on the base side. And it's really, really tightly regulated. If your body gets to 7.35, we say that you are experiencing acidosis. So if a person's in the hospital and they're not breathing properly, and you take the pH of their blood, you discover it's below 7.35, you say that person is experiencing respiratory acidosis. Their carbon dioxide levels are elevating because they're not breathing. They have an obstruction in the airway. All kinds of ways to do this. And I'm going to detail all of them for you in the spring. Respiratory and metabolic alkalosis and acidosis, the whole 9 yards. Okay. But I want to relate it to skeletal muscle contraction today so you can see how important all this stuff is tying together. Okay, so carbon dioxide means acid. And that acid is not good for human body function because anything below 7.35 and things start shutting down. You're not going to live long like that. So one of the major reasons for breathing is to blow off the carbon dioxide so that your pH stays around 7.4. Y'all see that? Now, let's walk this out. One of the most popular diet phenomenon today, there's a bunch of popular ones, but one of the most popular is a diet that removes sugar. So the first big popular fad with this was something called the Atkins diet, and there are lots of different versions of it now, the South Beach diet and others. And that diet asks the person who's going to lose weight to go through what's called an induction period. Basically, you go through about a 2-week, 10 to 14 day period of time where you don't give your body any glucose at all. No sugar at all. The only thing you give to your body is protein and fat. What happens whenever you do your body that way, you enter induction, your body enters a condition, and it says it right there in the first chapter of Dr. Atkins' book, your body enters a condition called ketoacidosis. This is a phenomenon that diabetics regularly enter into who are not treated properly. So a person with type 1 diabetes who doesn't make insulin has very high sugar levels, but they can't use the sugar, so they might as well not have any sugar in their body at all. And so their body converts the enzyme machine to get their energy from the carbons of lipids. And so their body becomes, because of that, enters into what we call ketoacidosis. Now here's why. Here's why that happens. Whenever whenever your body hydrolyzes fat, the fatty acids run through a reaction called beta oxidation. Now, I'm not going to teach you the reactions of beta oxidation either. They're interesting, but that's biochemistry. We don't need to do that. You need to know the name. And as a result of that beta oxidation, the body makes acetyl-CoA so that you can have energy. So, if you have no sugar, in the system, can your body actually use lipids exclusively to make energy? Yes. In fact, we learned at the beginning of this that muscles actually prefer the carbons of lipids, especially with low metabolism kinds of things. Low energy expenditures. So this beta oxidation thing is normal, okay? But I'm giving it to you as an example to try to help you remember it. This would be what would happen if you starved your body of sugar. Now, one of the products produced whenever your body is starved of the sugars and is producing acetyl-CoA through beta oxidation are molecules called ketone bodies. They're really small carbon units, but these little small ketone carbon units have a real desire to give away their hydrogens, which means they're acids. So as the ketone content increases, so will the free hydrogen levels. So I'm going to say it again. Whenever a diabetic or a person who starved their body of sugar needs energy, they produce that energy by way of beta oxidation. And in the diet protocol, they say your body is entering into a condition called, you hear it in the name now? Ketoacidosis. The ketone body levels are increasing, and they're acids, and so they give off free hydrogen, and your pH is declining because of that. And you say to yourself, what's the big deal? Why? I don't understand. Why would you care so much about that? Okay, so I'm going to draw for just a moment. So I need you to turn that to the board so everybody can see this. Okay. Why is that dangerous? Okay, now you guys learned this story, right? Dr. Moore told me that y'all were sick of hearing about sodium and potassium. Now, would any of you like to rat out your classmates and tell me who said that?
Rodney.
Cheyenne said that? He pointed at you. Danny said that? Okay, so the person who points is getting minus deductions on this. Okay, so you see this. I'm hoping at this point in your lives you see this and you go, I got you, dude. Sodium and potassium have to move through ion channels, and this is how things work, how muscles contract, how the nervous system works. I got you. Okay? So if I'm going to regulate the levels of these ions in the body, then I'm going to have an impact on how my body works, how muscles contract, how your heart works. And somewhere along the way, in my description of this, in my explanation, somewhere along this path, I told you guys that when you go to the hospital and you think you're having a heart attack, there's some things they're going to look for. Can you remember what I told you? Okay, so potassium levels is something they're going to look for. So I'm about to give you a little more with that in its relation to this story. The punchline, if you want to know, the punchline at the end of this is Dr. Atkins died of a heart attack. There's your punchline. So when people start telling me that they're removing all the sugar from their diets to force their body into ketoacidosis, this is the story I tell them. And I feel a moral obligation to tell you, because all of you will be in clinical settings. And somebody at some point in your life is going to come to you and tell you that they are going to do a no sugar ketoacidosis induction in order to cause themselves to lose weight. And then you're going to tell them this story. Okay, so potassium is one. Can you remember the others? So cardiac and skeletal muscle are anatomically the same, right? On the inside of the cells. So the whole story about calcium binding to troponin And myosin binding to actin, that's the same, right? So the muscle, the cardiac muscle, is deprived of oxygen, and it cannot make energy. So what does it do? Remember your energy sequence? Stored. What was the next step? What does that mean? Creatine phosphokinase. Y'all remember the creatine story? I'm trying, people. Are you guys going to be taking creatine supplements? You learned this? Okay. And then the third piece was the oxygen story, oxidative. So when I told you about the CPK, I said there's a cardiac version of this, and it's going to be elevated in a person with a heart attack. And then the third one that I mentioned to you was the protein, troponin, remember? Why is troponin so important? It's the one that pushes tropomyosin out of the way so the muscle can contract. So your heart will overproduce this and this if you have an oxygen deprivation. And you can measure it in the blood. Okay, so let's finish the story here. We're running out of time. Potassium levels and the lipid story. All right, in your kidneys, draw this picture in your notes. It will come up many times in anatomy and physiology. Let's do the top one, blood. In your kidneys, you have a tubular network. You have a tubular network where blood is passing through the kidneys and liquid from that blood is passing through a tubular network in the kidneys. Whatever comes out of your blood into these kidney tubes will end up in the urine. So this is a process that we call filtration. So you get stuff into your urine, passing out of the blood, and that's how you get rid of it. So that's how we make urine every day. Your kidneys produce about 178 liters of this a day, and we normally put about 1.5 liters in our bladders. So there's a lot more to that story, okay? But in addition to putting stuff out of the blood and the urine, there is a special mechanism late in the kidney tubule network that puts ions, specifically hydrogen and potassium ions, back in the blood. It's a protein that is capable of transporting hydrogen and potassium. Now, tell me, if you already know that your body lives at a pH of 7.4, and if you get below 7.35, you're in trouble, then you've got to know that there has to be multiple ways to keep the pH at 7.4. Now, one way you've already learned today that we're going to keep the pH basic is by, right? Because carbon dioxide is acid. So when you breathe, you are blowing off acid to keep the pH up at 7.4. But that's not good enough. We have to use multiple systems in order to do this. And your kidneys are one of those systems that do this. And one of the ways, there's two major ways in the kidneys. This is one of them. One of the major ways the kidneys regulate hydrogen potassium concentrations in the blood is with a protein in the tubular network that puts these two back in the blood. Now, normally, there's a balanced transport of hydrogen and potassium out of the kidneys back into the blood, where the kidneys prefer to leave the hydrogen in the urine and keep the body more basic. This is one of the fundamental ways the kidneys regulate pH, by transporting hydrogen and potassium, or not transporting it. Now, if you elevate, if you do something to your body to elevate the free hydrogen content if you do something to your body to elevate the free hydrogen content, you force your body into a condition that we call ketoacidosis. Leave it there a second. You force your body into a condition called ketoacidosis. The regulation of the hydrogen and potassium in the kidney will go off balance. And what you will end up with is an elevated level of potassium in the blood. Because the kidneys are going to tell your body, I cannot survive below 7.35, so I'm going to get rid of the hydrogen. So the kidneys start juicing the hydrogen out in the urine. So if you took the pH of a person who is experiencing ketoacidosis, you take the pH of the urine, it will be more acidic than it was normally. pH of urine is normally around 7, but you're going to get pHs around 6 and below, in the 5s, for the person who's experiencing ketoacidosis. Because the kidneys are going to be really pushing hydrogen. Because there's so much more abundance of it in the filtrate, it's going to be really pushing the hydrogen back into the blood. It's really pushing the hydrogen into the urine, really pushing the potassium back into the blood. So what you're going to end up with is a lot more hydrogen in the urine and a lot more potassium in the blood. All right? Last piece. Let's say you have a situation like this. This is the outside of the cell. This is the inside of the cell. Now, in order for the cell to develop a negative charge, what has to happen? In order for the cell to develop a resting membrane potential, what has to happen? You've got to establish a gradient, and then what? Why is it negative? Right, because potassium is diffusing out faster than sodium is diffusing in. Do y'all remember that? Why does potassium diffuse out of the cell? Because there's a higher concentration of potassium inside the cell. Now, what would happen if the concentration of potassium on the outside of the cell was artificially higher? So I have caused a situation here now where there's more potassium in the blood. The spaces around my cells will have more potassium in them. The potassium number out here is going to be elevated. So what will happen to the ability of the potassium to get out of the cell? What, Danny?
It won't be able to leak out.
It will not be able to leak out as fast. And so if the potassium won't leak out of the cells, what happens to the charge in here?
Positive.
It becomes more positive. How much more positive will it have to become before something happens? About, from the example we used in class, how many millivolts?
15 millivolts.
About 15 millivolts. Do y'all remember that? So if this is a heart muscle cell, and you are experiencing ketoacidosis, and you've caused an unnaturally high level of potassium in the spaces around your cells, and the heart itself now is becoming more positive. Are you following the sequence here? If the cell becomes more positive, it's more likely to contract. So guess what the average heart rate will be of an individual on ketoacidosis? Higher or lower? Higher, exactly. And if there's already some disposition, some precondition that has caused the heart to be oxygen deprived or some other cardiovascular event, and the heart begins to be stimulated in areas of the heart mass where it's not supposed to be stimulated because of a whacked out concentration of hydrogen and potassium, then the heart will begin to beat in an unorganized way. We call that, in a clinical setting, ventricular fibrillation. And you will not survive that. So if you go to the hospital, why? Why are they, so I think I'm having a heart attack. Why do they want to know about the potassium concentrations? Because they impact the resting potential of the cell. And the cardiovascular